Hello everyone. This day, today, tomorrow and next day we are going to work on chapter 6, Laplace transforms. And today we do section 6.1. Hello everyone. We are moving to chapter 6, Laplace transforms. Laplace transforms is another method which helps us to solve differential equations. And it has a special use, which we are going to learn. But for now, we need to know what is Laplace transform. Laplace transform is kind of linear operator, which transfers a function space into the space of Laplace transforms functions. So I'm going to start with definition of Laplace transform. Let me write it down. Definition. So give me a second, guys. I'll move it a little bit. Okay, I want to work somehow instead of P. I have a Laplace transform. Okay, give me a second. Hello, everyone. We're going to move to chapter 6, which is Laplace transforms, another method of solving differential equations. It has a specific goal to where actually the method is used, but for now we just need to start with definitions and with like easy stuff on Laplace transforms. So we are going to start with definition. Give me a second. Definition. Let's f of t be a function on interval from 0 to infinity. Well, I don't have infinity here, so I'm just going to write down infinity. Laplace transform of f of t is called f of s, and f of t is a small function f of t, right? And f of s is a big f of a different variable s, actually. And it's defined as improper integral from 0 to infinity of e to the power of minus st multiplied by f of t dt. So we actually take function f of t multiplied by exponential function e to the power of negative st. Here s is a constant, t is a variable, and integrate by t. After we do improper integral from 0 to infinity by t is going to disappear from integral, and the only variable which is going to be left is a parameter s. So my answer is going to depend on s, and the answer is going to be called Laplace transform. We also going to use f of s equals L and little f in curly brackets. That's another way to write down Laplace transforms. Okay. What else? I think that's all about definition, and we can move to kind of explaining how everything works. First, let me remind you what is improper integral. Well, you probably remember somewhere in calculus 2 or calculus 5b, you were doing integrals, for example, from 1 to infinity 1 over x squared dx. Why the integral is called improper? Normal integrals are going to have limits which are numbers. So integrals are defined on closed interval. This integral we calculated from 1 to infinity. Infinity is making this integral improper. Mathematicians created a trick to calculate these integrals without violating actually like idea of integration. They put at the top of the integral a variable like t, for example, or n. Well, you can label it anyway. And integral is becoming a proper integral. Now it's not integral from 1 to infinity, it's integral from 1 to t. They do the integration like definite integral, and then they calculate the limit when t goes to infinity. This way we satisfy both conditions. We take the integral, which is supposed to be between two numbers, and we bring t to infinity, which is going to make this integral from 1 to infinity. Of course, you probably remember from 5b class that not all integrals are going to exist. Some improper integrals are going to converge. Converge means that they are going to give you a number Like, for example, this one, let's calculate it. That's going to be what? Negative 1 over x. I'm going to substitute 1 and t and calculate a limit after t goes to infinity. Sorry, my pen is not perfect. So I'm just going to do it very, very quickly. Everyone understands that this is like antiderivative of 1 over x squared, right? So I'm going to do substitution. So it's negative 1 over t plus 1 over 1. And when we calculate a limit, that's just a little review of how we deal with improper integrals. And when we calculate a limit as t goes to infinity, this term will go to 0. And we are going to have our integral equals to 1. When we do have 1, integral is called convergent. Convergent integral is a good integral for us. So we consider only functions which are going to produce convergent integral here for Laplace transform. So actually not all functions are going to produce convergent integral. Let me give you an example of non-convergent. So I'm going to label this one convergent. Well, okay, let me show you something divergent. Integral from 1 to infinity e to the power of x dx. Let's calculate this one. That's a function too. Why don't we calculate the integral? So it's going to be a limit and the integral from 1 to infinity e to the power of x dx and t. Sorry, I'm supposed to write down actually over here t to kind of do improper integral. T goes to infinity. So we do know that integral of exponential function is exponential function itself, right? And we substitute limits 1 and t, and we do the actually limiting process after we do substitution. And we are going to have something like e to the power of t minus e to the power of 1. And if we bring t to infinity over here, we do know that exponential function at infinity goes to infinity, right? So our integral is going to be equal to infinity, and this one is divergent. Well, what is going to happen to this Laplace transform if it's divergent? The function is not going to have Laplace transform. Not all functions do have Laplace transforms. Okay, well, it's not necessary. Like my integrals here are different from the integral which I set up for Laplace transform. So people actually took care of lots of functions by multiplying by the factor e to the power of negative st. You know that exponential function is one of the fastest growing functions, right? We remember that if the power of exponential function is positive, it goes like this, and it grows fast very quickly, right? And if, sorry, should not put comma here, but if the function has negative in the power negative x, it's going to be looking like this, and actually is going to decrease very fast. So here we are dealing with case of increasing function, and of course area under this function is going to be infinity. But area under this function is going to be very nice, because if you calculate it from 1 to infinity, you're going to figure out there's going to be a certain number. So you see that not all exponential integrals are divergent. This one is divergent, but maybe there are some convergent, and some integrals from other functions can be convergent or divergent too. So we kind of did a review, right? Now I want to name a function which we use to do this Laplace transform for integration, because actually there are lots of other transforms which are done in a similar way. The function which sits over here is called kernel. So, sorry, I want to write kernel of transformation. Okay. Okay. Let's consider example which calculates actual Laplace transform. So I'm going to move everything up. Oh, it's not what I wanted to move up actually. Why did it move that? Oh, it doubled the integral. Well, guys, I'm sorry. I doubled my integral. Was not supposed to do this. I actually want to just kind of move everything up. Maybe I should use just like my mouse pad. Okay, I'm going to calculate Laplace transform of something very, very simple. By the way, doing Laplace transform is what? Let me kind of draw. So these are functions f of t. So we apply Laplace transform. I'm going to label it L, well, because it's Laplace, right? And we get another set of functions, f of s. So they are connected between each other, but they are not same, right? So function here and function here are different functions. They are connected by a special operator, but they are not same functions. So, well, you probably remember linear operators from linear algebra, right? Okay, I'm going to do example number 1 of Laplace transform, and I'm going to use a very, very simple function. F of t equals 1, just a constant. And I'm going to do the integral. I'm going to consider t greater or equal than 0 because we don't need actual Laplace transform beyond this, right? And I'm going to do the integral. Sorry, let me label it properly. So Laplace transform of f. We can also write down f of s if you wish. I'm going to use s as my variable, right? That's going to be integral from 0 to infinity e to the power of negative st multiplied by 1 dt. I just plug everything into my formula and kind of calculate the result. We do know what is integral of exponential function, right? And I'm going to just maybe continue over here. So I'm going to write down that's a limit as, well, here guys, because t is already reserved as my variable, I'm going to use a different letter to bring it to infinity. I'm going to use big letter N. I know that's not very convenient considering what I was doing before, but because t here reserved as a variable, I cannot use t as a limit too. It's going to be just messy. If you do understand that t here and t there is different t's, that's fine, but normally it's not very good to use same. So integral of exponential function is exponential function itself, right? Minus st. We have to divide this by minus s, because if we differentiate e to the negative st, you are going to get negative s in front, right? E to the negative st. So we divide by negative s, and I do substitution of 0 and n, right? So my upper limit instead of infinity is n, but then I will bring n to infinity. Well, after I do substitution, I'm going to get e to the power of negative sn minus e to the power of 0 is 1, right? And over here in denominator, I'm going to get negative s. And I will need to calculate a limit when big N goes to infinity. So, well, what is going to happen to e to the power of negative Sn? For s greater than 0, for positive s, the number will go to negative, right? Negative infinity. So I'm going to write down if s is greater than 0, the number over here is negative, the total exponent, right? And it will go to 0. So this term will go to 0 because at infinity, e to the negative infinity is equal to 0. So I'm going to just get minus 1 over s, which is going to give me a simple answer, 1 over s. Right, here I have s greater than 0. S greater than 0. What is going to happen if s is less than 0? Well, let's imagine s is less than 0, so it's like a negative number. Negative number and negative are going to make positive, n goes to infinity, so it's positive infinity, and that's going to be the case of infinitely growing exponential function or my improper integral, which is divergent. So actually I cannot have s negative here just because the integral will be divergent. Okay, guys, it's nice to remember certain Laplace transforms by heart. It's just going to be easier. You're not going to look up the table every time you need a Laplace transform. So my suggestion is to just remember that Laplace transform of 1 is 1 over s. Maybe I'm going to write it down somewhere in a different color and kind of circle it. So it's one of our first Laplace transforms. I'm going to write down Laplace transform of 1 is 1 over s. I'm also going to add a condition that s is greater than 0. Well, if s is equal to 0, what are we going to have actually? S equals to 0 is going to give us 1 minus 1 and yes, a denominator. We don't like it. So we are going to keep it strictly greater than 0, okay? When it's equal to 0, we are going to get 0 in denominator, which is not going to give us anything good. Actually, if you set it up over here equals to 0, that's going to give you what? Just 1. Integral of 1 from 0 to infinity is equal to infinity. So it's not because it's in denominator, it's because actually this integral is divergent by the nature. Okay, I'm going to circle this to make it like a formula. Now I'm going to do more examples because actually in this section I want to give you lots of examples like what are Laplace transforms of certain functions and then give you one theorem at the end, okay? So let me scroll this up and move to my next example. So my next, sorry, I want to scroll it totally up beyond that screen. I don't want to go actually that. Why? Okay, I don't care. Now, let's calculate Laplace transform of another function, which is also a very simple one. I'm going to return back to my green, example number 2. And that's going to be Laplace transform of t. What is Laplace transform of t? Well, let's just substitute everything. It's going to be integral from 0 to infinity. And we are going to have t, my function, right, multiplied by e to the power of negative st by the kernel, integrated by dt. Which is going to give us a limit n goes to infinity. Integral from 0 to n t e to the power of negative st dt. So I'm going to do the integrations and plug in the numbers and kind of get the final answer. So I'm going to move over here. So I'm going to keep the limit. By the way, guys, if you kind of want to take the integral separately, you can always take integral separately and then plug everything under the limit. Here I'm going to use integration by parts. You still remember how integration by parts is done, right? We assume that one of the functions, exponential, is a derivative and one of the functions is a function, right? So we calculate antiderivative of exponential function, which is kind of easy, right? That's going to be, we already did this, that's e to the power of negative st divided over negative s, right? And then we do minus, the formula is, let me remind you, the formula is f derivative of g dx equals f g. So we'll need kind of antiderivative of what we are thinking derivative minus integral of g derivative of f dx, right? So here is my f. I'm going to label it. This is my f and this is my g prime. So now I'll need copy g, which is going to be my f doesn't look like f actually, which is like my f is t, my g is negative e to the power of st over s minus integral, and I have to copy my g, which is negative e to the power of negative st over negative s, and multiplied by derivative of my function f, which is going to be equal to 1, and then continue integration by t. And what I'm going to have, well, this is just plain exponential function, very easy to integrate, right? I'm going to write down the limit, n approaches infinity, and over here t, e to the power of negative st over negative s. And here, well, I have so many minuses. I think this minus is unnecessary because this minus comes instead of this one, right? I'm going to erase this minus. So these two minuses are going to give me a plus, so I'm going to put plus here. Now, integral of exponential function is going to be the same like exponential function divided by negative s. So probably I should not put plus, but put minus again. Let me cancel the plus. So it's going to be minus e to the power of negative st divided over s squared now, right? One more minus s. Minus s are going to give me plus, and the minus, this minus is going to stay, right? Now I'm ready to do substitution of 0 and n to actually do my limit. So I'm going to start with n. I'm going to have limit n e to the power of negative n t over negative s minus e to the power of negative s n. Sorry, I plugged n in the wrong place. It's supposed to be actually s here. Sn, because my variable is t here. And Sn divided over s square. At 0, this term is going to be totally 0 just because 0 multiplied by anything is 0, right? This term is going to give me what? Plus, because it's supposed to be minus according to Newton-Leibniz formula, but because it has minus already, it's going to give me 1 over s square. Something like this, and n goes to infinity. So what we have right now, we have exponential function multiplied by n and just exponential function. I'm going to start with this one. What is going to happen to the limit here? Well, we already know exponential function was when n goes to infinity will go to 0 if s is positive. So I'm going to label somewhere as positive. Well, very good. So this one goes to 0. How about this one? Well, guys, exponential function and power function, when you multiply them and take a limit, exponential function is always the winner. You probably remember something what we call L'Hopital's rule, but I don't want to use it actually here. What I'm going to do, I'm going to write down this expression as n over minus s e to the power of ns. I'm going to put this one in denominator. Exponential function grows faster than polynomial, or any actually, like this one is linear, right? But any polynomial. So this limit goes to 0 too. This just grows faster. Okay, s here is a parameter. It's just a number, like 1 or 2 or 3. Just we need to make sure that it's greater than 0. Otherwise, this will not go to 0. This will go to infinity. Okay. So, sorry, I'm going to label this goes to infinity. This also goes to infinity. If you use L'Hopital's rule here, this one is going to disappear, this one is going to stay. So the total limit will go to 0. So we have 0. I'm going to label that I'm considering this one. We have 0. We have 0. I'm going to label what I use, L'Hopital's rule. This 0, this 0, this 0, this 0. So the only term which is left is 1 over s squared, which is a nice one, right? So I'm going to kind of change my color and write down Laplace transform of t. I'm hoping, guys, that you are going to remember at least like 5 Laplace transforms, which we do today. It's 1 over s squared and s greater than 0 again. Well, guys, interestingly, I'm going to scroll a little bit down to show you like the 1 is going to be 1 over s and t is going to be 1 over s squared. A little bit no traditional, right? The constant goes 1 over s and the first power going 1 over s squared, but not difficult to remember, right? Okay, so I think we will try to do Laplace transform now of exponential function. So let me scroll it up again. Why it does not allow me to scroll it? Okay, I don't know. It wants me to have something, I guess, written on the board. So my next example, let me change the color. Let's make it blue again. Example 3 is going to be Laplace transform of exponential function, something like this. E to the power of 2t. How about this? Well, let's write it down. It's supposed to be easy. Integral of 0 to infinity e to the power of 2t by e to the power of negative st, the kernel, dt. By the way, guys, if you remember this formula, you can always do this Laplace transforms just manually if you remember formula plus improper integrals. So what are we going to have? Well, first, let's combine expression under the integral. So I'm going to keep 0 at infinity until a little bit later. And we have e to the power of 2 minus s over here t and dt. Well, now I think we are ready to do the limit, so I'm going to put the limit as n approaches infinity. And what is the integral of this expression? It's e to the power of 2 minus s t divided by 2 minus s. If we differentiate this, 2 minus s by t. 2 minus s is going to be a constant sitting in front, right? So we need to compensate for it. And I'm going to put limits 0 and n. And I think I'm going to kind of write them down in and then explain what is going to happen to everything. So we have e to the power of 2 minus s n over 2 minus s minus, if you plug in 0 here, 0 is going to give me 0 and e is going to turn into 1, and I have something like 1 over 2 minus s. Well, this one does not have any n, just because it was plugging 0, right? For this one, we remember that exponential function goes to 0 only if the power is negative. We know that n is positive already, so what should be negative is 2 minus s, must be negative. Otherwise, it will go to infinity and the integral is going to be divergent. Okay? Convergent. Integral. So what does it mean? It means that 2 is less than s, or s is greater than 2. Remember, we had something like s greater than 0. Here, s is greater than 2, which is actually the power over here, right? What is going to happen if s is greater than 2? Well, this will go to negative infinity, which is going to bring the whole thing. So the power is negative. I'm going to goes to negative infinity, and the whole expression will go to 0, a little bit crumbled, but will go to 0. So we are going to have minus 1 over 2 minus s. I'm going to bring minus inside and write it like this, s minus 2. Well, looks very nice, right? So I'm going to write down two formulas actually. This one and more general one when you do have a over here. So let me use my red color. So Laplace transform of e to the power of 2t. Used wrong brackets. Come on. Is 1 over s minus 2. So guys, if you do have a here, I'm going to write down that s is greater than 2. If you do have instead of 2a, what is going to be? It's going to be that Laplace transform, more general formula, e to the power of at, can be any number here, is going to be equal what? 1 minus s minus a. I'm just plugging a instead of 2 in the final answer. And s must be greater than 8. So we kind of got a general formula. Every time you get exponential function, you don't need to take the integral anymore. You just can use the general formula. I don't know if I want to circle it. I think it's going to be too bad if I circle it. It's not going to give me a circle. So just a formula to remember. Maybe I'll circle this last one because it's like more general. Okay. So you see a nice formula for exponential function. Well, more examples. And again, guys, this lecture we are going to do actually almost all different examples. Just I want you to learn this. Let me scroll it up again, and I'm going to start with trigonometry. Somehow it never allows me to bring it too high. Okay, well, let's change the color. And example, it was 1, 2, now that's going to be example number 3. We are going to find Laplace transform of trigonometric function, something like sine, let's do. Sine of a t. You see, guys, I already want to get a general formula. I'm not placing here a number, 2t or 3t or whatever. That's going to be just the arbitrary constant a. And how Laplace transform is going to look? Well, let's write down the integral. The integral from 0 to infinity sine of at by e to the power of negative st dt, right? Now guys, what I want to do, I want to take the integral by itself first and do the substitution later. I'm pretty sure that you totally forgot how to calculate integrals like this. Well, maybe few people still remember, but not many, right? There are two different ways to do integrals like this, and I'll show you both ways, so you can kind of choose which one do you like to use. So integrals like this are integrated by parts, and if you remember from calculus 5b, we are using a method which is called looping. We are making a loop to calculate this integral. So we are doing, this is sitting in a section by parts integration, but we are going to actually do it twice. So what I'm going to do, guys, I'm going to do this integral and then kind of, I'm not gonna kind of give any comments. I'm just going to write down solution and I'm going to speed it up a little bit, okay? And then you are going to just see the final solution, okay? So again, integral is by parts. And I will start it and then kind of just do it fast, okay, without comments. So by parts means that I'm going to think that this is derivative, this is a function, so I'm going to write down equals e to the minus st divided by negative s. Okay, almost done. When t is equal to 0 here, it's 1. When t is equal to 0 here, it's also 1. So it's 1, it's minus a over s squared. But because we subtracted, that's plus a over s squared. Okay. Okay, now guys, I'm going to start bringing it to infinity. Well, again, if our s is greater than 0, this is going to be a negative number. Infinity here is going to bring me exponential function to 0, right? Sine is does not go anywhere, but it's going to be between -1 and 1. I'm going to write it down. Sine of an by absolute value less than 1. So it's limited by this, same as cosine of an is by absolute value less than 1. So if I multiply 0 by less than 1, you can use a squeeze theorem here. These two terms will go to 0. So I'm going to maybe change the color and kind of write down. This goes to 0, this is 1. Also, this is kind of maximum 1, this goes to 0. I'm not trying to say that sine will go to 1. I'm thinking that it's less or equal than 1. Maybe I should write it down instead of going to. So it's going to be more clear to those people who are copying it. Sorry, at least not the wrong. This goes to 0. So the only thing which is going to be left over is this one, which I forgot to copy. I'm going to copy it over here. 1 over 1 minus a squared over s squared. Let's just simplify it, and I think we're almost done. So we are going to have this term left and this one, the factor left, right? I'm going to just write it down. If I bring this to the common denominator, I'm going to have s squared minus a squared here, right? And s squared will go in numerator and cancel this s squared, right? There's a square, so it's going to be a on the top. Well, what I think, did I lose a minus somewhere? My notes are telling me there's supposed to be a plus over here, but I somehow accidentally have a minus. Let's say I kind of don't see where I'm missing a minus somewhere. Well, I'm going to fix it. I think the formula is supposed to have a plus here. Plus over here, which means that I miss minus somewhere here in calculations. Maybe this one, I think, yeah, there was a minus and minus and minus. Yeah, I see where I'm missing minus. So, sorry, that was supposed to be a minus. I just kind of missed one minus over here, because there are minus, 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 3 minuses. And then this minus is going to become a plus here, and because I did this in green, it's going to be a plus here too. Well, that's the final answer. I'm going to scroll it a little bit up and write it down. So actually, exponential, not exponential, but sine function is going to become what? Just a rational expression. I'm going to, let me choose my red color again. So Laplace transform of sine of at is going to be just a rational function. You see that so far, all my Laplace transforms are rational functions. They are not like actually exponential function or like polynomial functions or sine. You see, all of them are becoming rational functions, which is good for us, right? Well, Laplace transform is going to give you a uniform representation of the function. So I'm going to circle it. Now, guys, I don't want to do more in lecture, but I'm going to put one more function in my notes below this, because like taking it with like lecture makes no sense. Actually, I spent like 5 minutes just doing it in silence, right? So I think that's going to be all for today. On the next lecture, I'm going to consider piecewise defined function. Maybe I'm going to put it just as another example, but without lecture, okay? And that's going to be it, okay? So it's already 42 minutes long. I'm sorry that it took me too long to explain such a simple thing, but Again, there's going to be one more example here. I'm going to do the cosine, but I'm going to use a different method. Here I was using integration by parts. For cosine, I'm going to use a different method. If you like more this different method I'm using for cosine, use it. If you don't, you can use integration by parts. Do not memorize the formulas. That's the worst you can do. And I'm going to do one more example, which is going to be piecewise defined function, the function which consists out of two different functions, and how Laplace transform is going to work with it. Okay, and that's going to be it for section 1. Okay, I'm going to stop my recording at this point and kind of see you in section 2.